Okay, let's have a look at question 23. Question 23 from the Advanced Maths HSC paper 2024. Question 23. So here we are given a random variable which is normally distributed, mean is 0, SD is 1. Table gives probabilities that it is less than the particular z value. So this is the cumulative probability up to the z-score. We are told the scores in a university examination with a large number of candidates are normally distributed. The mean is 58, standard deviation is 15. So by calculating a z-score, find the percentage of scores that are between 58 and 70. All right, well, the mean is 58. So the x bar is 58. So for part A, we know that there are 50% less than 58. So we need to find a z-score for 70. Now, standard deviation is 15. So z-score is going to be equal to the score, 70, minus the mean, 58, divided by the standard deviation, which is 15. This is going to be 70 minus 58, which is 12 on 15. This is 0.8. So the z-score associated with a score of 70 is 0.8. According to the probability table, if z is equal to 0.8, this implies that the cumulative probability is equal to 0.7881. So between 58 and 70 will be 0.7881 minus 50 minus 0.5. So between 58 and 70, we should find that there are 28.81% of examination candidates. So this is part A. Now part B, explain why the percentage of scores between 46 and 70 is twice the answer to part A. Well, if we draw this curve, this is a bell curve, type of normal distribution, type of bell curve, looks like this. 58 is in the middle, 70 is 0.8 standard deviations up, 46 is actually 0.8 standard deviations down, 46. So 12 up to get to 70, 12 down to get to 46 from the 58. So whatever percentage is here, that percentage is the same here. So the percentage of scores from 46 to 58, the percentage of scores is the same as the percentage of scores from 58 to 70. So this is double 28.81. 28.81 times 2, 57.62. 57.62%. And it's to do with the fact that the bell curve, we're assuming it's symmetrical. Now for part C, we're told by using the values in the table above, find an approximate minimum score that a candidate would need to be placed in the top 10% of candidates. Okay, well, if we look at the probability table up the top, it tells us that if z is 1.3, then the probability, cumulative probability up to that point, is 0.9032. This is 90.32%. This is a pretty good z-score, minimum z-score associated with the people in the top 10%. So you would need a z-score of 1.3 or more to be in the top 10%, pretty much based on this table. We need to find what score corresponds to a z-score of 1.3. So the score itself will be the mean, 58, plus 1.3 times the standard deviation, which is 15. So this will be 58 plus 1.3 times 15. That's 77.5. So the minimum score a candidate would need to be placed in the top 10% is about 77.5. It's probably a little bit lower than that because this value, 90.32, was slightly higher. But an approximate minimum, a good approximate minimum is the 77.5 we just calculated. And that's going to be the solution that we have to this question. So when you do questions like these, because they are statistical, sometimes your answers can vary a little bit, right? You could say 77 or you could say 78. The table itself doesn't necessarily tell us that the exam only has whole marks. And some university examinations do not only have whole marks. They'll give you half marks or part marks, depending on what the questions are. So we don't actually know that's the case. So 77.5 is in theory possible. 77 is a good candidate answer. 78 is a good candidate answer. They're all sort of in the ballpark.